Hello everyone, this is our video demonstration about our Smart Pathfinder program, which is implemented using Python, used to find our shortest path and the path that requires the minimum time using the available algorithms. So the first thing I'm going to talk is about the overview. So the Smart Pathfinder is a Python program that computes the optimal routes between locations on a map represented as a weight graph. The system is designed to handle large-scale road with thousands of nodes and edges, supporting two distinct optimization criteria per query, minimizing total distance and also minimizing the total travel time. Each location in the network is modeled as a node, and each road as a directed or undirected edge carrying two types of weight, a fixed distance value, and a time-varying travel time that changes across 24 hours to simulate real-world conditions such as rush hours. The system accepts routing queries that may specify nodes or edges to avoid and returns two paths per query. One optimizes for distance and the one for travel time, along with full statistics for each. So the core algorithmic components for this program will including Dijkstra algorithm for minimum distance for pathfinding using a lazy deletion mean heap as its priority queue. We will also implement a star algorithm for minimum time pathfinding using an Euclidean heuristic derived from 2D node coordinates. We will also implement a custom binary mean heap implementing the priority queue used by both search algorithms. And finally, we will implement an agency list graph as a primary data structure for storing nodes and edges. And all data structures and algorithms are implemented from scratch in Python without the use of external libraries in compliance with the project constraints. So in order to run this project, we will need to verify that Python is installed in our machine. So we just need to type this command to verify that Python is already installed in our machine. And as you can see here, it returns the Python versions of our Python, of the current Python. So the next part of the video demonstration, our teammate will demonstrate how to use this program.
Now I'm going to demonstrate the main program. To run it, you type python main.py. Now the program will give you 4 different map size options. So our map is represented using an adjacency list. Since it can contain thousands of nodes and edges, an adjacency list provides better memory efficiency than an adjacency matrix. Here I'm going to go with option 2, medium map with 500 nodes. Now it's going to ask you for a source node as well as a destination node. Now it will ask you for a travel hour. So the time it takes to travel a path can vary depending on the travel time, with the period between 7 to 9 in the morning and 17 to 19 in the evening, the peak hours. This is similar to a real-life road network. So I'm going to go with it, which is the default. Next, optionally, you can also provide a different nodes to avoid as well as different edges to avoid. Now the program will output 2 different paths. First is the minimum distance path generated using Dijkstra's algorithm. The second is the minimum path, the minimum time path generated using A star. Here you can see the minimum distance path is shorter, while the minimum time path has a shorter travel time. Next, I will try the same query again, but this time I will provide a different travel time. Here you can see the minimum distance path is still the same, but the minimum time path is different based on the different travel time. Now I'm going to try the same query again, but this time I will provide a list of nodes to avoid as well. So I'm going to avoid these 3 nodes here. As you can see, even though it's the same query, it generated a different path in order to avoid the nodes provided here.
Run the our program in the demo mode to show the how it works with the provided query. So we will run our main file, but in the demo part. So as we see here, we have generate a handcrafted map with 10 nodes and 12 each. You can see the first query, we put the source is 0 and the destination is 9, the hour is 8. So the output of the program is the mean distance, which is the extra method is have the path, the distance, and the time. And the second one is mean time path. It's using the A-star methods. And it's also show the path, the distance, and the time. It also show the query times. So as we see here, the output of the minimum distance path is not the same as the minimum time path. That's the same in the first two nodes, but from the third and the fourth node, there's some different in the two methods right here. For the second query, we put an avoid node. Here is number 4 and keep everything the same as the first query. So at the above query, we see that the minimum time path have to travel through the fourth node. But because we put the avoid to travel through the fourth node here, there's a different part show out here. This return a different part when comparing with the first query. While the extra methods will return the same path and distance or time. For the third query, we change the hour to 17, and the destination is to the fifth node. So as we see here, there's two parts, but according to the minimum distance or minimum time is return the different parts. Once the extra will travel to the third node and the fourth node, while the A star will travel through the first node, not the third node. For the fourth query, we push the source is the third node and the destination is the second node, which will like kind of in the reverse way. But the program will still running successfully when it's returned the two part and the distance and the time and also the query times here. We also generating the large map with around 2,000 nodes and 4,871 each, and it might take more time to run this query, but it still return the path, the distance, and the time. And as we see here, there's still some similar in the two methods, but the paths will not always the same as we said before, and we can easily see that here on the the node 13, there's some different. So to summarize this demo session, our program is successfully processed different type of routing queries. It supports mandatory input such as source and destinations, and optional avoid nodes and avoid each. For each query, it returns both the minimum distance path and the minimum time path, including node sequence, total distance, total travel time, and runtime.
Smart Path Finder operates with absolute precision. We implemented a comprehensive unit testing suite to demonstrate query. I have opened the window PowerShell. Now let's add a CE test. Open dictionary. As you can see, instead of manual checking, we use the run our test I. This script leverages the unit test discovery mechanism to automatically find and execute all tests. Let's run the test. Test. Okay. As it shows, the code runs successfully through 19 tests. There are two core algorithms, the A-star and the Dijkstra. For the Dijkstra, we're verifying not just the shortest path, but also the avoidance logic. Tests ensure that when a node or an edge is blocked, the algorithm correctly reroutes the next best option over here. And for the A-star, we focus heavily on the heuristic assimilability. The test confirms that our Euclidean distance estimate never exceeds the true cost. A mathematical requirement for A-star to guarantee the optimal path. For the foundation, we have the mean heat in the graph. The safeguard of our priority queue and adjacent list, ensuring this low-level structure or bug-free is vital for the integrity of the search results. And for the map generator, we validate the rush hour logic, ensuring the travel times at 8 a.m. are appropriately higher than at midnight. Furthermore, in the test main, we use the mocking technique to stimulate user input. This allows us to test how the system handles invalid data or edge case automatically without needing manual interaction. In conclusion, with 7 specialized test files, we have created a robust safety net for our code. This gives us full confidence in the reliability of our path-finding results.